Good morning to one and all present here. It is my pleasure to welcome everyone to our valuable webinar. We are in the third session of Day 2 International Webinar on Recent Trends in Pure and Applied Mathematics. I invite Professor Mr. Wibeski for giving an introductory address.
Good morning to all. I am Beski, Assistant Professor of Mathematics in this institution. I will give the introductory address to our resource person, Dr. S.K. Vaidya. Dr. S.K. Vaidya, presently working as a professor at the head of the department of Saurashtra University, Rajkot in India. He has a rich experience in 34 years mathematical research and teaching. He has supervised 30 students for MPhil and 23 students for PhD. Currently, 6 students are on the path of PhD degree under the supervision of Dr. S.K. Vaidya. Till now, he has published about 205 research articles, research papers in national and international journals. Then he also a member of the editorial board of the journal like Mathematics Today and journal Computational Mathematics. He is a vice president of the Academic Discrete Mathematics for the period 2022-22. He also his area of specialization is graph theory, especially leveling graph, domination graph, and graph energy. Next, I would like to Dr. S.A. Vaidya to deliver the speech about the topic. Thank you, sir.
So thank you for my introduction. Good morning to all of you. I am very much thankful to the organizing committee of this 3 days international webinar on recent trends in pure and applied mathematics, organized by SYED AMMAL Arts and Science College. As all of us are very much aware that theory of graphs has witnessed unprecedented growth in last century. And the main reason is its applications and the potential to solve many real-life problems. Theory of graphs is very convenient to represent any real-life situation by means of graphs. So today we will have some of the ideas about some potential fields of research in graph theory. Next, I will share my slides with you. My screen visible to you, Anita? Anita?
Yes.
Is my screen is visible to all of you?
Yes, sir, it is.
Okay, fine. Then I will proceed. Thank you for your kind help. So, some potential fields of research in graph theory. So, what is the importance of studying mathematics as this 3 days international webinar is focused on pure and applied mathematics? Then what is the importance to study the mathematics? In most of the sciences, one generation tears down what another has built, and what one has established another undoes. In mathematics alone, each generation adds a new story to the old structure, as told by Hermann Hankel. Then, before we proceed to know some of the potential fields of research, I would like to share historical background of the evolvement of the theory of graphs. Is Leonhard Euler, and it is supposed that the systematic presentation of the Königsberg problem by Leonhard Euler during 1736 is supposed to be the birth of graph theory, and it was the graph drawn ever in the history of graph theory. And the problem was to find a walk through the city that would cross each bridge once and only once. The island could not be reached by any route other than the bridges, and every bridge must have been crossed completely every time. And one could not walk halfway onto the bridge and then turn around and later cross the other half from the other side. And the people, for the people of that time, it was fun, it was challenge, and people were trying to solve this problem. And this is the graph and the situation of the problem depicted by Leonhard Euler. Then other milestones of this theory. In 1840, systematic presentation of four-color problem by Mobius in one of his lectures, and 1847, theory of trees by Kirchhoff. Kirchhoff was physicist, and all of us have studied the Kirchhoff's law of electricity. And to avoid short circuit, the concept of trees were used by D.R. Kirchhoff on any electrical network. And we know that trees are the acyclic connected graph, means two wire of the same charge will not meet, otherwise it will be the short circuit in the electrical network. And at present also, the concept of trees is used in any electrical network. And in 1857, systematic definition of trees by Arthur Kelly, and Arthur Kelly published a paper on four-color problem in first volume of Proceedings of Royal Geographic Society during 1879, and in 1920, a first book on graph theory by D. Koenig. And presently, it is the year 2022. So, in just 102 years, the graph theory has made its space in mathematics as well as in science. In 1958, domination in graphs as a theoretical subject was formalized by Claude Birch, and in 1967, concept of graph leveling was introduced by Alexander Rosa. In 1976, Wolfgang Haken and Kenneth Upton obtained an affirmative solution of four-color problem. And presently, there are many potential areas of research within graph theory, but I have picked up only three out of that. One is labeling of discrete structures. Other one is theory of domination. And the third one is the chemical graph theory. Then labeling of graphs. Labeling is a term used in technical sense for naming objects. Just we name the object, we label the object, that is called labeling. Using symbolic format drawn from any universe of discourse, such as set of numbers, algebraic groups, and the power set of a non-empty set. and the complexity involved in having a desired kind of leveling of a discrete structure usually arises due to the constraint inherent in the conditions required to be imposed as well as the nature of the universe of discord from which the levels are chosen. So, with that of sets we are considering, to select levels is also an important thing, and it is the core of the concept of leveling. And at present, many leveling techniques are available, and some potential leveling are graceful, harmonious, cordial, and magic leveling, prime leveling, etc. Here, in today's talk, we will highlight some major graph leveling techniques. So, what is graph leveling? It is an assignment of numbers to the vertices or edges of both, subject to certain conditions. And what is the nomenclature or characteristic or common ingredients in any graph leveling technique? One is a set of numbers from which the vertex levels are chosen. A rule that assigns a value to each edge or vertex. And a condition that these values must satisfy. So, we will have some glimpses of graceful leveling. A graph G with order means number of vertices and size means number of edges. Here we use the notation P and Q for order and size of a graph. It is said to be a graceful if there exists an injection from a vertex set to the set 0, 1, 2 up to Q, means starting from 0 and up to the size of the graph, such that the induced function from the edge set to the set 1, 2 up to the Q, Q is the size of the graph, means number of edges, defined by the absolute difference of vertex levels, and this function is a bijection, and F is said to be graceful leveling of G, and the graph which emits a graceful leveling is known as a graceful graph, and the concept of graceful leveling was introduced independently by Rosa and Golan. Here we have a graph which is known as the complete graph on 4 vertices, and here, according to the definition of graceful leveling, the leveling is shown. Then, for the advancement of the discussion, we will introduce the definition of decomposition of a graph. A decomposition of a graph is a list of subgraphs, such that each edge appears in exactly one subgraph in the list. Means decomposition is a collection of subgraphs in which no edge is common. Then, based on this definition, Rosa proved one result, that if H is a graceful graph of size n, then K12 plus 1 admits a cyclic H decomposition. Then there is a conjecture known as the Ringel's conjecture. In mathematics, conjecture means if it is a result which is supposed to be true, but its proof is not available. At the same time, there is no counterexample to disprove it. It is known as the conjecture. So K2n plus 1 can be decomposed into 2n plus 1 copies of an arbitrary tree T of size n. Is just now, at the beginning, I have mentioned that a tree is a cyclic connected graph, means it does not have any cycle. Here we consider K2n plus 1 means K5 where n is 2, 2 into 2 plus 1 means 5, so K5, and how we can decompose into 3T of size n. 2n plus 1 means 5 copies of 3, each of size 2. Let us see here. It will, as I click, it will display the copy. At the same time, to verify that there is no common edge in each tree, it will also change the color in the graph K5, and here it will be displayed. So these are the 5 copies of tree T, and we can say that we have decomposed K5, K2n plus 1 here, K5, into 5 copies of tree, each of size 2, each of size 2. Then Korzyk's conjecture. Korzyk's conjecture states that all trees are graceful. To prove that, proof is not available, just several attempts have been made to prove the trees up to certain order they are graceful, but not in general. And that's why it is a conjecture which states that all trees are graceful. Then Ringel and Korzyk jointly posed a conjecture that truth of Korzyk's conjecture implies the truth of Ringel's conjecture. In fact, the truth of Korzyk's conjecture implies the truth of a conjecture proposed jointly by Ringel and Korzyk, which states that for every tree T of size n, the complete graph K2n plus 1 has a cyclic T decomposition. Now, we will see the gracefulness of some standard graphs. The gracefulness of cane. Cane is graceful even only if n is less than or equal to 4. So, the complete graphs which are graceful are only 4. K1, that is a vertex. K2 means a path of length 1, that is P1. K3 means complete graph on 3 vertices, and K4. These are the only complete graphs which are graceful. So these are on the one extreme of the connected graph. Means there is the fundamental result that a tree with n vertices has n minus 1 edges, and a connected graph will have at least n minus 1 edges. So trees are on the one extreme of a connected graph, means a connected graph with minimum number of edges, while the complete graphs are on the other end, which have the maximum number of edges. A graph is complete if all of its vertices are joined by an edge. So In this interval, that is between three, that is a connected graph with a minimum number of edges, and the complete graph which is a connected graph with maximum number of edges. In between, there is a beautiful result proved by Paul Ardis. He was a Hungarian mathematician, graph theorist. He proved that almost all graphs are not graceful. Means there are some graphs which are not graceful. So it is always interesting to find out the graceful labeling, or to prove that, or to identify the graphs which are not graceful. So Rosa also identified three parity conditions. That why a graph G fails to be graceful. Either G has too many vertices and not enough edges. Too many edges, like complete graph. And wrong parity means both the conditions 1 and 2 hold simultaneously. That is the wrong parity. And that's why it is known as the parity condition. In accordance with the third reason, Rosa developed a strong parity condition and proved that if G is a graceful Eulerian graph, then Q congruent to means is size, number of edges congruent to 0 or 3 mod 4. Means the graphs with Q congruent to 1 or 2 mod 4, they are not graceful. This condition serves as a sufficient condition for non-graceful graph. This is the necessary condition, but we can say that the Eulerian graph with Q congruent to 1 or 2 mod 4, they are not graceful. So it confirms the existence of a subclass of a non-graceful graph. So whether a graceful graph can be embedded as a subgraph of a graceful graph or not, this type of problems as well as NP completeness problems are also studied by the graph theorists. Acharya Rao and Arugam proved that any graph G can be embedded as an induced subgraph of a graceful graph. So that is the thing. And any triangle tree, there is no subgraph in a graph which is K tree, that is the triangle tree graph. In a triangle tree graph, G can be embedded as an induced subgraph of a triangle tree graceful graph. And any planar graph, a graph is said to be planar if no two of its edges meets except the endpoints. So that is the definition of a planar graph. So any connected graph can be embedded as an induced subgraph of a Hamiltonian graceful graph. A graph is said to be Hamiltonian if it will have a Hamiltonian cycle. So that is the thing. Any connected graph can be embedded as an induced subgraph of a Hamiltonian graceful graph. And any connected graph G can be embedded as an induced subgraph of a graceful graph G1, where domination number gamma is the notation to denote the domination number. So the domination number of G1 is the larger graph, super graph of G. So gamma G1 is equal to gamma G plus 1. And total domination number, that is gamma G1 is gamma T G1 is equal to the total domination number of the given graph G plus 2. Means it will exceed 2. So the problem of deciding whether the domination number or correspondingly total domination number is less than or equal to k is NP complete even when restricted to graceful graph. So if we take the subgraphs of a graceful graph and we discuss the domination number, then the problem of deciding whether the domination number or total domination number is less than or equal to some k, then it is an incomplete problem. And we have one more corollary of the same type, whether the clique number is the order of maximal induced complete subgraph is also, means deciding the clique number for a graceful graph is also a NP complete problem. Then our own contribution is also there. Generally, I am dealing the problem in the context of various types of graph operations. Means we will either construct a super graph by means of various graph operation or construct a subgraph by means of various graph operations. So these graph operations are duplication. If we have any vertex vk, then all the vertices which are adjacent to vk, now they are also adjacent to vk dash, means the neighborhood sets of both the vertices are same. Then this type of operation is known as the duplication. And the graph obtained by duplication of an arbitrary vertex of Cn admits a graceful labeling. So it preserves the graceful labeling. This is the graph obtained by duplication of vertex v1, and then we have v1 dash, and the vertex v4 and v2, they were adjacent to v1. Now they are adjacent to v1 dash also. Then we have a weaker version of graceful labeling, which is termed as cordial labeling. Here, the vertex labels are chosen from the set 0, 1. And the induced edge label are also either 0 or 1, and the absolute difference between the number of vertex labels with 0 and 1 and the number of edge labels 0 and 1, they differ at most by 1. This cordial labeling is also known as equitable labeling. Means number of vertices with labels 0 and number of vertices with label 1, they differ at most by 1. Similarly, the same type of condition for edge labeling also. And if these conditions are satisfied, then we say that the function f is a cordial labeling, and the graph which admits cordial labeling is known as a cordial graph. This concept was introduced by I. during 1987. and many researchers from India also have explored this leveling. Now, the interesting thing is to enumerate, means on the given number of vertices, how many non-cordial graphs exist. That is called the enumeration of non-cordial graphs. The analogous result for cordial graphs, which is analogous to the result which we have quoted for graceful leveling. Here we have a result proved by Kehit, is an Eulerian graph with number of edges congruent to 2 mod 4 is not cordial. Means we have to find out the number of edges, the number of graphs on the given number of vertices. And we will use here the procedure which is known as Havel-Hakimi procedure. So, before I start the discussion, I will like to mention that the degree sequence. It is the degree sequence means the list of degrees of each vertices. It is known as the degree sequence. Now, whether it is possible to construct a graph from the given degree sequence, so it is always not possible. And the sequence which realize the graph, degree sequence which realize the graph is known as the graphic sequence. So whether the given degree sequence is graphic or not, that we can know with Havel-Hakimi procedure. So here the description of it is given, taking into consideration the simple fact that sum of degrees is 2. That is the fundamental theorem of, or hand-shaking theorem of graph theory. That is, the sum of degrees is 2. So, because each edge has 2 vertices. So, taking into consideration the simple fact that the sum of degrees is 2, we generate all the even partitions of 2 using the software Maple 10. Then Havel-Hakimi procedure is used to check whether the degree sequence is graphic or not. Just now I mentioned a degree sequence is said to be graphic, it realizes a graph. Then we say that it is a graphic sequence. Here we have the number of edges, that is the size of a graph is 6. There are 11 partition of 2e, means 10, number of sum of degrees will be 2e according to the first theorem or the fundamental theorem of graph theory. For e is equal to 6, there are 11 partitions, 12, 10 to 8, 4, 8 to 2, 6, 6, like that. There are 11 partitions. Out of these, which degree sequence or which partition will realize a graph, that we will see. We found that sequences 4 to 2 to 2, that is the 5 vertices. One is of degree 4, remaining 4 of degree 2. Similarly, all the 6 vertices of degree 2 are the only graphic sequence. So the graph related to 4, 2, 2, 2, 2 is the first one. It is also known as the bow tie graph, while other one is the C5. So when we have E is equal to 6, then we have this graph. So there are 2 graphs on 5 vertices which are not cordial. So when E is 10, then there are 42 partitions of 2E is equal to 20. All even partitions, means we are considering only Eulerian graphs. A graph is said to be Eulerian if all of its vertices are of even degree. And these are the partitions. And we found that the sequences here listed, they are the only graphic sequences. And the related 8 non-cordial graphs are here. These are 4 and remaining 4 are in next slide. Now we have listed down the number of graphic sequence and number of partitions. And surprisingly, if the number of partitions, means even partitions, are 5604, number of edges is 3, so 2E is equal to 16, 5604 partitions are with even numbers. Out of that, only 780 partitions are degree sequences are graphic, means they realize the graph. Means there are 780 graphs which are non-cordial, having the number of edges 30. So in this way, one can enumerate the non-cordial graphs. As I told you, one more potential field of research is theory of domination. Theory of domination. Then dominating site is the graph theory itself originated from a challenge or puzzle. In the same way, the theory of domination, that is the subfield of theory of graph, evolved through the game of chess, where goal is to cover or dominate various squares of a chessboard by certain chess pieces. In 1862, de Janisch considered the problem of determining the minimum number of queens. According to the game rules, queen can move either horizontally, vertically, diagonally over any number of unoccupied squares, provided there is no other chess piece lies in its way. And 2 queens on a chessboard are said to be attacking if the square occupied by one of the queens can be reached by the other queen in a single move. Otherwise, they are called non-attacking. Here, the arrangement of 5 attacking queens is shown, which can cover all the 64 squares according to the game of chess. These are five non-attacking queens. Five non-attacking means minimum 5 pins can cover all the 64 squares of 8 by 8 chessboard. The connection between the chessboard problem to find the minimum number of queens and dominating sets in graph is immediate. The 64 squares of a chessboard are the vertices of a graph G, and 2 vertices means squares are adjacent in G. If each square can be replaced by a queen on the other square by a single move. And domination as a theoretical subject, as we mentioned, by Mudge and Slot Mudge and R in 1960. In 1977, a detailed survey on domination theory by Cochrane and Harith Niami has received considerable attention because it has provided a source of reference for the researchers. Then what is dominating set? A dominating set is a subset of a vertex set of a graph such that every vertex in V is either an element of S or it is adjacent to an element of S. And then we say that S is a dominating set. Then minimal dominating set. A set is said to be minimal, or any property is said to be minimal if we consider that property, then no proper subset have that property. While every superset have that property, then we say that that property is minimal. Here, the property is the minimal dominating set, and we denote it as AMD as minimal dominating set of G. Minimal dominating set of G. Here we have a graph and the dominating set we will find out of various cardinality. It is a dominating set of cardinality 3. Here we have the blue colored vertices form a dominating set of cardinality 4 and graph having minimal dominating set of cardinality 5. Means if we remove any blue color vertex, then some vertices will not be dominated, and then it is minimal. The domination number. The domination number gamma G of a graph equals to the minimum cardinality. Means among all minimal dominating sets, if we consider the set with minimum cardinality, then or equivalently the minimum cardinality of a dominating set. And the upper domination number, the gamma G, that is the maximum cardinality. Here the graph we have considered, the small gamma G is 3, while upper gamma G or the upper domination number is denoted as capital gamma G, and it is pi. Then one important question is how one can relate a dominating set of a given graph with its graph complement. That is an important challenge. The complement of G, denoted as G bar, is the graph with vertex set V, in which two vertices are adjacent in G complement if they are not adjacent in G. That is the definition of graph complement. Then the dominating set which works for the graph itself and its complement, graph complement, then it is known as a global dominating set, and the corresponding domination number is known as the global domination number. Here we have a graph C5 for the global domination number V1, V2, V5. They are the vertices of a dominating set in C5 as well as its complement, which is just drawn near to it. So the vertices V1, V2, V5, they belong to the dominating set of a given graph G as well as its complements G complement. Then the dominating set with this characteristic is known as the global dominating set, and the corresponding number, that is the minimum cardinality, is known as global domination number. Here, for the given graph, the dominating set is of the vertices V1, V2, V5, and its global domination number is 3. So these are some existing results, that certain things just for the sake of to get the idea of the existing results, these are displayed. This problem to find out global domination number is NP complete. The concept of total global domination number global dominating set was introduced by Cooley and Janaki Raman, and they have also characterized the total global dominating sets. And we have also contributed a lot in this field. Here some results are displayed. This is one of the important things, that S is a global dominating set of Pn that is path on a n vertices, if and only if it is a global dominating set of Pn dash. So now we have in the next 5 to 7 minutes are in my hand. So I will just give a glimpse of very emerging fields of recent times. That is the chemical graph theory. Why it is important? Because it is a frontier between two important fields of science. These fields are the chemical science or chemistry and mathematics or mathematical science. So what is chemical graph theory? The theory of graphs is a branch of discrete mathematics, as we have seen, that deals with the way objects are connected, the way the objects are connected. And the connectivity in a system is an important characteristic of graph theory. While in chemical graph theory, one can discuss the connectedness of connectivity in chemical graph. So such graphs are served as a model for any understanding of molecule and reaction scheme in chemical transformation. The graph provides simple rule by which chemists may obtain very qualitative prediction. That is the characteristic of any molecule or its structure can be discussed, and one can get idea from the graphical representation of molecular structure. Every chemical molecule can be represented by means of corresponding molecular graph which represent the constitution of molecule. It is a very well-known organic molecule, that is propane C3H8, and its molecular graph is shown just adjacent to it. Here it is an isomer, means number of atoms are same, but they have some different connection, and that's why it is known as the isomer. So cyclopropane, and here is chemical graph is shown, or molecular graph. So what we'll do, each vertex of the graph corresponds to an atom of the molecule, and two vertices are adjacent if there is a bond between the corresponding molecule. So we are interested to simplify this notion. In order to simplify the handling of molecular graph, every carbon atom is represented by vertex and carbon-carbon bond by an edge, while hydrogen atoms are ignored. The neglect of such atom may cause any change? No. It will not change the structure. So, the neglects of hydrogen atoms and their bonds cannot be cause of an ambiguity. Such graphs are known as hydrogen suppressed graph. Here, the same graph, that is propane C3H8, and its hydrogen suppressed graph is shown. Here we have already defined what we can call by the hydrogen suppressed graph. For the same cyclopropane, the hydrogen suppressed graph is shown. The concept of graph energy is a frontier between mathematics and chemistry, and it is defined with the help of hydrogen suppressed graph of a molecular graph. So we have some basic definition. For that we need the knowledge of adjacency matrix of a graph. All the entries of adjacency matrix of a given graph G, or the entries of a simple adjacency matrix of a simple graph, all the entries are either 0 or 1. It is the entry is 1, element is 1 of the matrix, then if Vi is adjacent to Vj and 0 otherwise, means it is not adjacent, then we put 0. Spectrum. Just it's a way of writing the eigenvalues, because the adjacency matrix is a square symmetric matrix, and one can obtain the characteristic equation for that, and the solution of this characteristic equation is known as the eigenvalue of the graph. So it is the way to write the eigenvalues with its multiplicities. Means how many eigenvalues are same, that is called the multiplicities. So it is known as the spectrum. So lambda eigenvalues are with a multiplicity m1 and so on. The energy of graph is the sum of absolute values of its eigenvalues. That we said that it is the energy, and the concept of energy was introduced by Goodman, who is the professor of chemistry at Serbia, and he introduced this. Then the natural question arises. This is the only question we will tackle. Looking to the crunch of time, 2 minutes are left. How graph energy is affected by various graph operations. If a new graph is constructed from the given graph, then how the energy of both the graphs can be related. Then our investigations are for the splitting graph. For more clarification, a graph C4 and the splitting graph of it is shown here. Again, it is the concept which based on the duplication of a vertex. Here, if all the vertices are duplicated all together, then the graph is known as splitting graph. And here the splitting graph, which is denoted as S dash, it is shown here. And similarly, shadow graph, we have V1 and V2. V1 is adjacent to V2 and V4, and the new vertex is also adjacent here. It is called shadow. Means two copies are taken and make them adjacent. That is the thing. So if we take M copies, then it is known as M copy, M shadow. Then the important thing is the energy of a splitting graph of G is √5 times energy of G. It is very important result, and this result is already published in a journal whose editor is Ivan Gutman. The name of journal is Match, Journal of Mathematical Chemistry. And we have an M splitting graph. This was called the splitting graph, but if we consider M splitting, the definition just we had shown, it is 1 √1 plus 4m times energy of G. Similarly, for M here, the energy of 2 splitting of C4 is demonstrated. Similarly, for the two shadow graph, the energy twice energy of graph G, and then we will have the I will end this talk by this quote by Maya Angelou, that what he caught, I have learned that people will forget what you said. Just I have said, and after lunch or before lunch, you will forget. People will forget what you did, but people will never forget how you made them feel. I am sure that I have tried to feel you better, and that you will remember. I am very much thankful again to the organizing committee of this 3 days international webinar for giving me a chance to interact with this august audience on this virtual platform. Thank you, one and all present over here. Thank you.
Thank you, sir. Queries are invited from the participants.
Thank you, sir, for your words of knowledge. Now I request Professor Besky to deliver the vote of thanks.
It is such an honor for me to get an opportunity to thank to all. On behalf of the Mathematics Department, SYED AMMAL Arts and Science College, I extend my gratitude to our respected research person, Dr. S.K. Vaidya, who explained about the topic, some potential areas of research in graph theory. We are really enlightened with your knowledge and presence. Your thoughts have truly inspired us and making the webinar interesting and meaningful. Thank you, sir.
Thank you.
Next, I am happy to express the vote of thanks to the participants such as professors, assistant professors, research scholars, and students of our and various colleges who have made this webinar in a great success. Once again, thank you all for your cordial cooperation. The next session will be held on 3 p.m. today. Thank you.